is okay for you. If anyone wants me to maximize this a little bit, just please ping me on the chat. All good. Okay. Thank you, Barry. Okay. So yeah, welcome to session 6, I believe. Let me just go through the summary. So I'll just make a brief comments about the current module, and then we go briefly through a recap of the key concepts that we need from the previous lecture, and then we'll go through the stuff, the new stuff. Really, maybe for some of you this is not new because you're already coming from an advanced background, but hopefully for most of you on the audience, this will be new stuff for you. If not, maybe you will see it, the stuff in the different, hopefully in the different perspective. So it will be a very brief session anyway. And then I'll do a comment about the study materials. So that's it really. So in terms of the foundation module, for those of you who are just joining us today, or those who are watching us for the first time on YouTube, this is the foundation module. There are 2 more modules after this one, which are a little bit more advanced. The difference is essentially in this module, we are focused on finite dimensional Hilbert spaces, whereas in the advanced modules, we will be dealing with the infinite dimensional case. So that's it really. The green stuff is the stuff that we went through already. So the yellow is the ongoing. We are here. So this is the first session. There are 2 sessions, as you already figured it out. The hashtags are the number of sessions. So we are here today. I just want to make a brief comment. Some of you might have noticed I forgot to kind of comment on this for the past 2 lectures. I added a session here on the complex Hilbert spaces section. This is essentially just after going through the introduction and so on about Hilbert spaces, just to have a session where we will go through the axioms of quantum mechanics, really, or the postulates, whatever you call them. I call them axioms because mathematics is what we are interested in. So, and it will be just more about kind of seeing how the modeling is done, more of that than really discussing, foundational stuff. So this is not a way to discuss, it won't be a place to discuss the foundation of quantum mechanics or even to, I would say, learn physics, because it will be mostly about, the modeling side of things, giving a system, what does the rules tell us about, how to model the system in terms of states, observables, and these things. So it will be more of a shut up and calculate type of approach, if anything. But maybe in the fireside chats, I might invite a physicist who worry about the foundation of quantum mechanics to have a fireside chat with you guys. But that's all I wanted to add about this. So yeah, let me just check the chat. So there's no question about the slight changes that I did. You're all happy about the axioms of quantum mechanics. Okay, good. Okay, cool. Thank you. Okay, another thing I want to share, especially because we have new sign-ups. They might not have gone through everything, all the other lectures. In fact, this is one of the things that maybe soon I will stop inviting new people to join in, because it's just very hard unless they have they already know some fundamentals. It will be very hard for them to catch up. So yeah, anyway, for the new people joining this, we are essentially in a linear algebra section, or maybe another way to call this is possibly abstract linear algebra. So there are 2 approaches for the time being until we get to Hilbert spaces section, where everything will converge to one approach. The live sessions hopefully will be a little bit more abstract and more algebraic, and also more tailored to quantum mechanics and quantum computing in particular, whereas the study materials are a little bit more tailored to some sort of undergrad linear algebra textbooks. So And it's not tailored to KM because it deals with general vector spaces, whereas in our case, we are mostly interested in complex vector spaces, in particular Hilbert spaces. But nevertheless, for the time being, anything that, all the stuff that, the materials that I share with you will contain relevant stuff. It's just they are working in general in any field. You just, in our case, in the live session, we'll be working with complex field, but it doesn't really matter. However, once we get to the Hilbert spaces section, then I will share new materials that will be more aligned to the live sessions. Okay, so yeah, so the live session for the time being will be a little bit more abstract. This is to help prepare those of you who are going to attend the next module, which is a little bit more abstract, the functional analysis module. So where you have to deal with very strange looking operators and very strange looking Hilbert spaces. So, where, you can't draw things on the plane and these things. So algebra will be your best friend, okay? Another thing before we jump is, this is really, some of you who attended the fireside chat a few days ago. I don't even remember which day. Was it? Yeah, Tuesday, with Amira Bass. She said something very interesting that I think really resonates with this module, which is, I'll quote her here. I think it's really important to have this mindset of not being intimidated by things that you don't know, but rather be excited about things you don't know. So this is really, I think, as a motivation as things get harder, hopefully you will kind of have this as a kind of a motivation for you to keep going, even as things get a little bit harder as we go along. Okay. Check the chat. Tuesday, yes, thank you. Some of you might know in the UK we are on lockdown, especially in the region where I am living at the moment. We are on lockdown, so it's very hard when you don't go out to kind of keep up with the days. So let's recap last session. I hope you all had the materials and the slides, and if you didn't attend the session, hopefully you did have the time to go through the YouTube. So one of the things that you really need to wrap your head up around is the concept of linear independence. So which is defined as this: when you have a sequence of vectors psi1, psi2 to psi n, they are linearly independent if they satisfy this condition here, right? And we saw also an example that these two are typical prototype of linearly independent vectors in C2 in this case. And for those of you who attended the previous lecture, the new guys joining, this is the Dirac. We already started using the Dirac notation. So if you are struggling with the Dirac ket notation, please go back again, watch the thing. It's essentially just place the size inside the brackets. That's it. And this is a special convention, particularly for those who are interested in quantum computing. This is the 0 qubit, the 1 qubit. So just in case the new guys, if you are like finding it a little bit strange. Another concept is the concept of basis. In this case, Hamel basis. As I mentioned last time, there are two concepts of basis for finite dimensional vector spaces, which this module is all about. We don't really need to make a distinction between Hamel basis and the Schauder basis, but a basis is essentially a special set of a subset of V whose elements are linearly independent. Okay, you already know what linear independence means, so that means the element of the basis are linearly independent. And another condition for a basis is that they span the entire vector space V. Or another way to say that any element, any vector in V can be uniquely written as a linear combination of the elements of the basis. And then there is an example here of C2 when we take V to be C2 and B to be this subset of C2. And I hope this is not a problem. You figure it out. This is a basis, and then I ask whether there are other bases, and I think you already know yes. The answer is yes. By the way, I think there was an exercise in the slides asking. I gave a list of vectors. Did you find any bases in that list? I can guarantee you there are at least 2 pairs that could form a basis. I hope you did. If not, that's fine also, because we will come across them once we reach the Hilbert space section. Okay, so far this is all good, right? Nobody has any questions about bases. Yeah. Okay, so what differentiates Hamel basis from other type of bases? This is not something that we have the vocabulary for me to say this. In the functional analysis section, you will be able, I will be able to discuss this more. Okay, it's to do with the accountability of bases and so on. You know, for finite dimensional, because the bases are accountable, you don't have to make any distinction in these things. Whereas for infinite dimensional case, you have to be very careful what sort of basis you deal with. In quantum mechanics, in particular, we need to deal with the separable Hilbert spaces, because A, they have countable bases. B, they have the bases are orthonormal. So yeah, I don't. You will see on the functional analysis section why. Okay. Yeah. Okay. In fact, in most textbooks, they just assume, people, they don't distinguish the different, the different distinction. I mean, quantum mechanics textbooks, they don't distinguish the difference between Schauder and Hamel bases, even when they are dealing with infinite dimensional Hilbert spaces. Okay, so another important concept is that of dimension of V. So the dimension of V is nothing more than the cardinality of the basis. So giving a basis, the dimension of V is just the cardinality. So the number of elements of V. So in this case here, we can see the dimension of C2 is 2, because this is a basis of C2 and the cardinality is 2. Okay, and we can also generalize to Cn, as a lot of you have already figured it out. And then next week, hopefully, you will also see this thing, that 2 vector spaces are, they have the same dimension if and only if they are isomorphic. And yeah, later in the tensor product also, you will see why, even though you construct this, instead you work with this, because they are obviously the 2 spaces are isomorphic. Okay. Here's a proposition that I think you guys can prove this, or if you have any issues, go to the chat. I can maybe help you, but ideally you help each other. It essentially says, if you have 2 bases, B1 with the elements E2, with elements E1, E2 to be En, and then you have another basis, B prime, with the elements E prime 1, E prime 2, blah, blah, blah. Then the cardinality of the 2 bases is the same. So in other words, N equals M, okay? So this is why I think I mentioned in the last session that all bases have the same cardinality. So the notion of dimension is a well-defined notion. It does not depend on your choice of basis. That's great, right? Because it would be a nightmare if you have to define the notion of dimension, based on what basis you pick, right? It would be very strange, right? So yeah, so this is also not a problem, I assume. Yeah, cool. If it's a problem, just type on the chat. Soham is not here today to kind of thing, and I'm sure Barry and the rest will be helping. Okay, so let's go to linear operators 101. First of all, before we go through the definitions, normally in standard textbooks, they don't use the term operator. They reserve the term operator to when you deal with the Hilbert spaces or Banach spaces. But because we are, in our case, in this module, we are interested in Cn, and Cn is already a Hilbert space. In fact, it's also a Banach space. it doesn't make any difference for us. We can just start using the term operator as opposed to linear map. So, but they mean the same thing. Okay, in the study materials, the author uses the term linear map. I'm here using the term linear operator, even though we haven't reached Hilbert spaces yet. Okay, so a linear operator is nothing more than just a map from V1 to from V to W that satisfy these two conditions. T of psi1 plus psi2 is the same as taking T of psi1 plus T of psi2. Okay, and the same with scalar multiplication. So essentially, linear maps they respect the vector space structure. This is what you really, from a mathematician point of view, this is very, very interesting. This is a type of maps that because as a mathematician, giving a certain mathematical structure, you are interested in maps that preserve such a structure. In our case, this is the vector space, the linear structure. So we are interested in linear maps that respect this structure. If you are doing topology, you are interested in homeomorphisms, which preserve the topological structure. If you are, say, for example, doing differential geometry and this thing dealing with manifolds, you are interested in something we call diffeomorphisms, or diffeo. If you are in a canteen having a coffee, you don't say diffeomorphism, you just use the term diffeo. So structure preserving maps are really important because they also enable mathematicians to classify objects. So that's why linear operators are very important for us. So a convention also I will do is, instead of writing T of psi like that, like you normally do when you evaluate a map, I'll just write T psi. Okay, so this means the same thing. Okay, sometimes I might use both when the notation, when it's convenient to do so, especially because of the Dirac-Ket notation. In fact, you will see an example where it's convenient to use both because otherwise it will be a little bit more confusing. Okay, so, and then we have this, before I look at the chat, we have this first proposition, which I will leave it to you for homework. I think you can do this. Otherwise, you can also see the proof of this in the study material, or version of this, is that if T is a linear operator and from V to W, and B is a basis of V, then B prime defined as this, as taking acting the operator on B, on the elements of B, is also a basis of W. Okay, so that's it really. That's all what a linear operator is. Based on this definition for the thing, can you think of anything that before there's the next slide? I'll go through example. Can you think of anything that can be like a linear operator? Not necessarily for the advanced audience guys, for the guys who are advanced. What could be a linear operator? Say, for example, when we take V equals W equals C. By the way, there's nothing to prevent us from making the V and W to be equal, because there is no restriction on in that respect. So V and W can indeed be equal. So in other words, we can deal with just one vector space, linear operators on itself. Okay. It depends what you mean, the thing. Ideally, something that we already have vocabulary to think about it. We talk some of the stuff that we went through the previous lectures. Because people will think when you say rotation, what's rotation? We haven't defined rotations yet. So Francisco is asking if B, do the E primes have to be there? Let me check. Did I do a typo or something? Ah, yeah, there is a mistake here. Yes, well spotted, Francisco. So there's a typo here. I didn't notice. So this is I will update the slide. So this is not. It wasn't meant to be beta e prime. Okay, so this is it meant to be e. So remove the primes, because obviously the operator is acting on the e's. So sorry for that. It's because copy and paste in LaTeX, and sometimes you forget to think. So I will update the slide. So thank you for that, Francisco. So the answer is no. This is actually a typo. It meant to be instead of e primes, it meant to be just e's. Okay, sorry for that. Okay. Okay, so let me just go to example. So let's let V equals W, and again equals C2, and let M2 of C be the ring of 2 by 2 matrices. You remember in the ring section, and it's defined as this, with it's like a 2 by 2 matrix, with entries in C, right? So we can build a linear operator out of any element of M2 of C as follow. So for any vector psi in C2, let TA act on psi like this. So essentially just like the matrix multiplication. Hopefully there is no typo. If there is, let me know. So yeah, this is a linear map. Does anyone have any doubts that this is a linear map? No? Okay, that's great. No one has any doubts. Okay, so a very interesting question is that since we've seen for C2, we can generate a linear operator from 2 by 2 matrices. Can we generalize this to Cn? In other words, so Mn of C. This is the later in the next session we will define it, generalize this. So it's essentially the n by n matrices over C. Really, yes. The answer is yes. We can construct a linear operator for each matrix in Mn of C that can act on Cn as a linear operator. Okay. So this is true. And then another question is, what about the other way around? If we are, say, giving an abstract linear operator, that's not necessarily a matrix, can we generate, can we construct a matrix representation of that? The answer is also yes. In fact, I think in the next session, we will also do that. So yeah, you can easily see how actually working with Cn is very, very handy, because if you need linear operators, the first thing you can think, the first place you will probably go to is the set of matrices, the square matrices, right? N by n matrices, because any element of n by n matrix forms a linear operator. Likewise, if you are working with an abstract linear operator, you want to do some computation, maybe it's very hard to do that in the abstract sense. What you might want to do is to encode that linear operator into a matrix, right? To make life easier for you. Okay. So let me check the chat. Does anyone have any questions or doubts about this so far? Okay, just the convention, okay. Okay, so this is a convention we'll do. So, when we have a matrix, n by n matrix, acting on Cn as an operator, we don't write Ta, like we just write A, but it is to be understood that it's representing we are taking it as an operator, okay? So, that's what I meant here. So for each, by convention, any operator that we generate from a matrix in Mn of C, we will just use the term. We won't write like Ta like this. We'll just stick to the thing. Okay, so it's just to be understood that we are using it as an operator. Okay. I mean, these are some of the stuff that actually we don't. Maybe I didn't even need to mention this. It will become like obvious that giving a matrix, I'm using it as an operator. But just in case, because some test books are a little bit confusing, or they might not, they might not assume that you are coming from kind of a background that understands this. Okay. Oh, here's an example why I was saying I will use the both notations in here, for example. So giving a linear operator T from V to W, this is the following. The following is true. So T of 0V equals 0W. Okay, so I've labeled this. So this 0V is the 0 in the vector space V. Okay, so the 0 vector. And this 0 here, this 0W is a 0, the 0 vector in W. Okay, this is another thing is, especially with the Dirac notation, it becomes very confusing because you can easily mistake this with the 1 qubit, with the 0 qubit, right? But just that's one of the reasons why I labeled V and W, just to so it's not confusing. In fact, some authors don't for the 0 vectors in some test books, they won't even put the 0 vector into inside the cat. They will just write 0, assuming that you understood from the context that this 0 here is the 0 of this, and this one is this 0 is the 0 of W. Okay, so you will be able to verify this. Okay, so I will leave this as a homework. If you have any questions, any doubts, and these things, I encourage you to go through to the Gitter channel. If nobody can help you, I will step in and help you with that. Okay, let me check before I go to the next definition. Okay. Another important concept is that of range. So giving an operator from V to W, the range is defined like this. So all the elements of W that are mapped from an element of V. And it's not hard to see. So in the set theory, this would be the image. Remember in the first session when we called it, the image of a map. Well, this is the same here, but the only thing now we are not dealing just with the plain set. We are dealing with the set containing the structure, the linear structures. So in this case, we decided to call it something else. So we're going to call this range of T, and range of T is a linear subspace of W. You can easily prove this. Remember from the previous session, I think it's session 4, to prove something is a subspace, you only need to prove two things. That the addition is closed in the subset, and that the scalar multiplication is also closed. Okay, so in this case, all you have to prove is that if you have two elements of the range, if you add them, the result is yet another element of the range. You also need to prove that if you have any element of the range and you multiply it by a scalar, then the result is also an element of the range. Okay, so that's all you need to prove to prove that this is a subspace of V. Another thing associated with the range is something called the rank. So the rank of it, obviously it's a subspace, it means it's a vector space itself. So therefore the concept of dimension also applies to it, right? So the dimension of the range is called the rank of T. Okay, this will be coinciding if some of you coming from, maybe a first course of linear algebra or something, you have the concept of, the rank of a matrix and these things, So is the abstract analog of that. Let me check. Any questions about this? I told you it's going to be very easy session today. No, okay, cool. Okay, so another important thing is the definition of a kernel. So giving a linear operator from V to W, obviously, the kernel of T is all the elements of V that are mapped to 0W. So all the elements of V that take you to the zero vector. Okay. So in literature, I believe in the study materials that the author does not use the term kernel. Instead, is null space, but it essentially means the same thing. They are using kernel because later in at least in mathematical physics, at least as far as quantum mechanics is concerned, most textbooks are normally use the term kernel. So in functional analysis and these things, this is the most predominant thing as opposed to the null space. So just to let you know, it means the same thing. And as you might guess, so the range was a subspace of the target space. Now the kernel is actually a subspace of V. So again, to prove this, all you have to prove is to prove the two conditions, right? That addition is closed in the kernel, and that scalar multiplication is also closed in the kernel. Okay. Let me check the chat. Any questions about the kernel, the concept of kernel? I mean, so far, a lot of these concepts, like it's just definition, and these things. Later, in the context of Hilbert space, we will come to this. We'll put more into context a lot of the stuff that we are going through. It might seem like very boring and these things, but at the moment we don't have the stuff, all the tooling and these things to be able to precisely kind of show you why they are useful. Okay. So let me check the chat. Yes, thank you, Barry, for helping on the question. On the study materials, you can actually see more of the thing. And once we get to Hilbert spaces, some of these concepts that everything that we went through will start to become a little bit more, okay? Can be a little bit more put into context, okay? And then we have this. You notice I'm no longer using the word proposition. Instead, this deserves to be called theorem, okay? So it says that given a linear operator from V to W, the dimension of V can be decomposed as dimension of the kernel of T plus the dimension of the range of T. This is very interesting, isn't it? Okay, so this is often called the dimension theorem. It's a very fundamental result. In fact, in the next session, in the next week, we will see some of the consequences of this. So this is very important concept, theorem, result. It might sound like the thing's very simple, but it's very, very important. And often also it's called the rank nullity theorem also, okay? So this definitely deserves to be called theorem. So it's the first theorem, or the first thing that we call theorem in our, since we started this, this module. And hopefully as we come closer to Hilbert spaces, we'll have more things that deserve to be called theorems. Well, propositions are also theorems, but it's like, you know, I will only call theorem stuff that are really, really like important stuff. So let me check. Okay. Does anyone have any, I mean, at this stage, you know, there's not, next week you will, you know, we'll go through more like the consequences of these things, and, you know, it will probably be less dry and less boring, hopefully. Move on. So, as a home challenge, before we wrap up, as I said, today is a very short session. Given these operators, some of you will recognize this, especially the guys coming from quantum computing. Why not, you know, wrap your head, you know, scratch your head and try to find the kernel of each of these operators, you know, and also find out what's the dimension of each kernel, right? You already know the dimension of V, you know. You might even look at the dimension theorem to see, you know, if you know the dimension of the kernel, you will certainly know the dimension of the rank, right? Sorry, of the range. So I really encourage you to kind of, you know, go think about it. And it's also important because, you know, even if you know, you don't find anything interesting, even if it's the result in the end, whatever you think will be like trivial stuff, at least by thinking about it, you know, you are internalizing with these things, you know. So it's really important, regardless whether, you know, the stuff is trivial or not, for you to, you know, get your head into these things. So the same for range. So look at the operator and, you know, go and construct the range of each operator and find out about the dimension. Obviously, this is very easy. If you start here, you know the kernel and you already know the dimension of V is 2, then obviously it's a piece of in the cake. And most importantly, feel free to use software, you know, so you don't have to the thing to aid you in your finding. If you need to do anything that can help you get your answers, feel free, you know, NumPy, SymPy, and whatever, you know. So after all, this is a way also for those guys, the developers, you know, on the audience, you know, say if you wanted to submit a work, you wanted to contribute an open source stuff just to get the certification and these things, you know, by starting to, you know, seeing, you know, playing with the software, you know, is a way. Maybe you will see some shortcomings that some of the software that you are using needs. Maybe you can go and contribute, you know, add something to the community. So I really encourage you. Let me check. Okay. Okay, thank you, Barry. Okay, so this brings me to the study material. Let's stick with the linear algebra done right. And in this case, pages 51 to 57, you should focus. And I must tell you, it does have some of the stuff that we didn't cover today, but we will cover next week. But nevertheless, it's good if you can wrap your head ahead of time. Maybe it will become easier for you because, you know, maybe the way I present the stuff will be different from, you know, the way he does present it. So for the time being, we'll stick with Professor Axler. But once we get to Hilbert spaces, then we will say goodbye to him. I'll give another reference as a study material. Another thing I wanted to comment is Thank you so much for those of you who have followed us on YouTube. So now we have a custom URL. So, you can just go YouTube and Zyko group. It's much more easier for us now to share the YouTube URL as opposed to just say, you have to search. So thank you so much for those of you who have followed us on YouTube. The session will be, the study materials will be uploaded. I will correct the slide on the basis stuff. And thank you, Francisco, for alerting me for the thing. And then please join the Gitter community, especially in some of the challenges, some of the proofs and these things. If you need help or you can't get your head around something, if nobody can help you there, and which I encourage you to help each other on the channel. So yeah, that's it really. I hope you enjoyed the fire. For those who attended the fireside chat, I hope you enjoyed the session with Amira. I certainly found it very interesting and very inspiring. And I'm working to get another fireside chat, and I'll get one of you, maybe Barry or someone else, to be the host if they are available. I will keep you updated maybe next week. It's a little bit hard because of the lockdown. It's like people are a bit thing with schedule stuff, but at least we had our first fireside chat. So I'll keep you updated anyway. With that, thank you, Anne, for the thing. So Amir is asking, is lockdown there a new lockdown? Yes, it's a new. Well, in the UK, they are doing like a regional lockdown. So they divided the lockdowns in tiers. There's like a tier 2, tier 3, and we are in tier 3, which is the more severe tier. So it's a little bit confusing. There is like some politicians saying, maybe we should have more kind of a national policy as opposed to have these regional stuff. So where I am is actually tier 3. But funnily, if I decide to move and go somewhere else, I visit a friend or something in another tier, then I'm not constrained. So yeah. Anyway, that's it for today as far as the session is concerned. I know we didn't cover much, but things are starting really to change of basis. We will go through all of that as we go along. And some of the stuff, even next week, there will be things that maybe we won't cover. Because at the end of the day, we want to get Hilbert spaces as soon as possible. And once we get to Hilbert spaces, a lot of the stuff that were left out will be put into the context of a Hilbert space. Okay? So, okay. Oh, moving base, changing of base. Okay. I understood now, Amir. It's a nice joke. Okay. Does anyone want to have any questions? I can actually pull one of you if you want to add any comment for the community or something that you want. I can bring you on the thing. Does anyone want to say anything to everybody or to myself or something without chat and these things? Feel free. I can pull you in. You can introduce yourself and say something. Don't be shy. Okay. Okay, no problem. No pressure. Yeah. So that's it, really. I'm just trying to see if I have anything else that I can add, but I don't think I have anything else. If I do, I will add it in the next session. So for the time being, thank you so much, and I'll see you next week. Okay, thank you. Thank you all. Okay, thank you. Have a nice week.